All right, so I'm Dr. Hartman, a self-proclaimed jackass with a PhD, and by that I mean I'm going to make mistakes fairly regularly. If you see something that doesn't seem legit, let me know and we'll sort it out. My office is across the street in Nethkin Hall 211, and my office hours are Tuesday, Wednesday, Thursday, and Friday from 1:30 p.m. to 4 p.m. I'm also involved with this organization right here, Eta Kappa Nu. This is the Electrical Engineering Honor Society, and we do circuits tutoring in Nethkin Hall, room 105. It'll be on Tuesdays and Thursdays from 2:30 to 4 p.m. I should be there as often as I possibly can be to help out with all of that kind of good stuff as well. That'll be like the engineering 221 students, circuits 2 students. You guys, if you choose to utilize it, effectively anybody that has any questions about any type of circuit can come up there and ask people who arguably should know things. Okay. All right, so in the event of a disaster, weather, emergency, etc., the class is expected to continue on using, that says Moodle and Zoom, because I forgot to update it to Canvas. So it'll be Canvas and Zoom, and I'll sort that out and the links and all that kind of jazz in a little bit. So the course objectives for this class is really to take what you learned in Mr. Gill's ELET 221 class and apply that towards power systems. So we're going to start by looking at single phase power systems, then move on to polyphase power systems with a specific focus on 3-phase systems, which is how electricity is distributed in pretty much all industrialized countries. And then from there, we're going to take a look at transformers, how they work, and then how transmission and distribution networks as a whole work. And that'll lead us into your next power class where we look at electric machinery and all that kind of good stuff. Let's see. So the textbook officially for this class is Electrical Machines with MATLAB 2nd edition by Tur and Gorin. I hope to God none of you guys have wasted your money on that textbook because it is hot garbage. So you may have noticed that we are currently on Zoom and that I am recording literally everything. So realistically, you don't need a textbook or anything like that for this class because all of the lectures and all of that kind of stuff will be available for you online and all that kind of jazz. For the majority of the class where we're doing circuit analysis and all of that kind of good stuff, if you just desperately need a textbook, you can go to Google and search CAD space ULABY, and the first link here brings you to a textbook called Circuit Analysis and Design by Fawad Ulabi and a couple of other folks. This textbook is absolutely free. It is distributed by the authors for free so that you're not stealing anybody's intellectual property or anything like that. That being said, I'm sure you're all aware you can just download textbooks off the internet, stuff like that. This one is given to you for free. It is actually quite good. So if I were to suggest a textbook for the majority of this class, this would be the one that I would actually recommend to you all. Wrong thing. All right, going back to the syllabus. Disability disclosure. If you need classroom or testing accommodations, please let me know as soon as possible so we can get all that kind of good stuff sorted out. The attendance guidelines are, I think I forgot to update this part too. It's actually policy 2206. Effectively, since this is a Tuesday, Thursday class, you're expected to be able to miss 2 days unexcused without having any issues. That's the official policy. The unofficial policy is that you all are adults and you're paying for my expertise. If you choose not to show up for that, that's on you, not on me. I'm going to take roll every day because I am obliged to do so. But for the most part, your attendance will not have any impact on your grade other than, you know, if you're not here, you're probably not going to understand what's going on. That being said, if you are on the borderline between 2 letter grades, so let's say that you're at like an 89.2 and you're wondering if I would be willing to bump you up to a 90 to give you an A instead of a B, the only thing that I'm going to look at to make that assessment is what your attendance looks like in this class. So if you're showing up It's very likely if I haven't seen you in 3 weeks, the answer is a definitively no, okay? Another thing that I want to point out just really quickly here, because I am recording everything on Zoom and have a Zoom link set up, all of you are welcome to attend the class over Zoom if that's the way that you would prefer to do it. However, with regards to attendance, if you are not physically here, you are not being marked as present on the roll sheets. So you need to be here and able to participate and ask questions and all of that kind of good stuff if you want any leniency with your grade. All right. Academic honor code is pretty boilerplate stuff. Being a student of higher standards, you pledge to embody the principles of academic integrity. And then we go into a little bit more specifics here. With regards to behavior, the official policy is here. My general unofficial policy is that if you're less of a condescending asshole than I am, you're doing great as far as your behavior goes. With regards to cheating, I do not care for that at all. I do not enjoy filling out the paperwork and sending students to the honor committee and all that kind of stuff, but I have to do it roughly every quarter. So just do yourself a favor and don't cheat. All right, homeworks. So a brief 3 to 5 problem homework set should be assigned and posted to Canvas at the end of most lectures. Homework assignments are to be submitted electronically to Canvas and completed using proper engineering format. I want to make a specific caveat here. I don't need a discussion section. That stuff never made any damn sense to me whatsoever. It works because math works. We're good. Okay, so if you write the problem statement down and all of that kind of stuff, provide me with your solution. That's all I'm looking for. There's really not any need for discussion as far as I'm concerned. Let's see. If you don't adhere to the proper engineering format, you'll be penalized. Late homework assignments will incur a 20% penalty for each day that they're late. Generally speaking, I'm going to try to give you guys, I think, 4 days to work each homework set. So that's realistically like maybe a problem a day kind of thing. I don't think that's an insurmountable amount of work to ask of you all. So that's what I'm looking at. In-class assignments. So for those of you that have had me before, particularly in Engineering 221, you're vaguely familiar with this. Nobody wants to listen to me talk for 2 hours straight, including myself. I am extraordinarily vain and conceited, but even I know 2 hours of me is a bit too much. So typically speaking, I'm going to wrap my lectures up somewhere in the ballpark of an hour to an hour and 15 minutes, and then we're going to spend the remainder of our class time working problems. So I've got your first in-class assignment up here. I'm going to try to have the following in-class assignments up before class so that you can print them off yourself and all of that kind of good stuff. These in-class assignments are literally just a way for you all to judge what part of the lecture you understood and which parts of the lecture you did not understand for whatever reason, and then you're able to ask questions about them in kind of a low to no stakes scenario. Is that my soldering iron? Awesome. So these in-class assignments, they are not graded for completeness, nor are they graded for correctness. It is literally just effectively a participation grade. It is for you to not have to listen to me, to get some experience trying to work problems and all of that kind of stuff before you attempt your homework assignment so that you can sort out what parts of what I covered made sense and what parts didn't make sense so that you know what to ask questions about. That's literally it. These are going to be due prior to our next class meeting. So if we go over here to Canvas really quickly, in-class assignment number 1, we have the online submission portal right here. It's due March 19th, which is our next class meeting, and it's due at 8 a.m. You can't see the 8 a.m. thing here, but effectively it's due immediately before the next class starts. That will always be the case, okay? So the expectation is that you will complete as much of the in-class assignment as you can before the next class meeting. Realistically, you should be able to do it actually in class, which is why it's called an in-class assignment. Turn it in, just whatever you have completed, and then we'll take that as good enough to go on to the next bit of material. I keep going to the wrong thing. All right, exams, there's going to be 3 exams. All exams are closed book and closed notes. That closed notes thing is probably going to be, I'll allow you to write an equation sheet kind of thing for it. 1 page front and back. We'll talk about that more specifically when we get a little bit closer to one of the exams. Only FE approved calculators are permitted for usage during the exams. A list of FE approved calculators can be found at that link. All right, so now you're gonna have to listen to a nerd rant about calculators for 5 minutes. How many of you guys currently use a TI-30X calculator? Okay, so not a huge amount of you, but for those of you that do, it's time to step up and get a not peasant calculator. Those calculators are the hottest of garbage for the amount of math that we are going to be doing in this class. Okay, so I'm going to talk to you very briefly about calculators that I think are good for this class and the subsequent classes, at least, that I'm going to teach. I am in no way, shape, or form paid by TI or Casio, but at this point, I probably should be. So my personal favorite calculator is the TI-36X, okay? I like this calculator a lot because it can do practically all of the complex math that we're going to be doing in this class very, very easily. It doesn't care if you input numbers as polar form complex numbers or rectangular form complex numbers or some combination thereof. It can handle all of that, and it can do it without having to actually switch the mode of the calculator. So this is my personal favorite. Okay, TI-36X, currently still in production, all that kind of good jazz. Another good calculator for those of you that for whatever reason don't want to go with a TI would be the Casio 115. This has a similar feature set. I personally don't like it as much as I like the TI just because you have to literally change the mode of the calculator to process complex numbers. And I'm lazy and don't like having to go from complex mode back into normal calculation mode over and over and over again. So that's the only reason I don't particularly care for this one as compared to the TI, but I have it and I know how to use it if any of you have any questions about it. And then we have the Casio 991. So for my Circuits 1 students, this is the one that I recommend to them the most because it's the only calculator that's FE approved that is capable of solving a 4-equation, 4 unknown system. These two can only do 3 equation, 3 unknowns for when you're applying nodal analysis, mesh analysis, and all that kind of stuff to DC circuits. Because we're not going to be really bothering with DC circuits, that advantage here is lost. So effectively, it's just a slightly fancier version of the 115. And this particular version of the 991 is actually discontinued by Casio, and I have not had an opportunity to buy the newer version just yet. This is a really good calculator. However, I just want you to be extremely aware. Right now, you can effectively only buy it used because it's been discontinued. If you see it used for $20, I guarantee you it's not a real one. And I say this from experience from students last quarter who bought a knockoff off of eBay that looks almost identical to this and literally just gave math errors constantly, regardless of what you were trying to put in. It looks almost perfect. It does not actually do the math. So just be very, very careful if you are choose to buy this particular calculator, because you might have to buy it off eBay and it might not be a genuine product. Okay, so just wanted to make you all aware of that. All right, rant about calculators over. Yes.
What would be the best place you say to buy?
So I feel like Walmart carries the TI-36 and the 115. I think our bookstore does as well. Amazon. Realistically, any of those places, you should be able to get either the TI-36 or the Casio 115 for between $20 and $25. Yeah, they're not prohibitively expensive. And if for whatever reason you can't afford that, you don't have to announce that in front of everybody, but you can come see me privately. I have, I think, 3 or 4 of these and 3 or 4 of these. So if you need to borrow one, you're welcome to borrow one. All right, so no cell phones during the test. I think that's pretty self-explanatory. Here is how the grades break down in this class. So the homework is worth 30%. The in-class assignments are worth 10%. Exams 1, 2, and 3 are worth 25% each. And then the weight of the exam on which you receive your lowest score will be reduced to 15%, meaning that you can have one bad test and it won't hugely impact your grade. So if you add all of that together, it comes out to be 105%, which means there's literally half a letter grade worth of bonus, if you take it that way, built in to the class. So realistically, there's not any reason why anybody who's putting in the work should not easily pass this class because there's already guardrails in place to help you out. Okay. The grading scale used for this course is a traditional 10-point scale. Given here, like I said earlier, there will be no curving or rounding of grades offered in this class. That being said, if you're on the borderline and you are attending regularly and all of that kind of good stuff, I'm willing to hear your case. If you're on the borderline and you're not attending regularly, pound sand. Let's see, syllabus changes other than the few typos, or that's not really typos, but I need to go back and change Moodle to Canvas and a couple of things like that. I don't anticipate that there will be any other changes to the syllabus, but if there need to be, I reserve the right to make them as long as I tell you about them. Emergency notification system stuff, sign up for it so that you'll be notified if the university has to close for emergency reasons. Make sure, trying to remember what setting I had to mess with when there was that stabbing in the fall that I didn't find out about until 5 hours after it happened for whatever reason. So just make sure your settings are up to date and that you opt into text messages and all of that kind of good stuff. COVID-19 policy, you could effectively just read this as a sickness policy. The long and short of it is I will be furious if you get me ill. So if you're sick, stay home and participate in the class over Zoom. If I get the flu or COVID again, I'm going to be so friggin' pissed off. So, all right, counseling services are available if you need them. And then I have the kind of boilerplate AI tools and usage policy, which there aren't really going to be any opportunities for that in this class, but these are the permitted and prohibited uses if you care to look at them. And then we have our tentative course schedule where I have all 3 of our exams and all that kind of stuff already mapped out. As you can see, I've effectively broken the class up into 3 modules, the first on single-phase systems, the second on 3-phase systems, and then the third on magnetically coupled circuits. So that's really what we're going to be focusing on as we transition into electric machinery in your next power class. Any questions, comments, or concerns regarding the syllabus? Yes.
So you said that you recorded all of your lectures. Are they posted somewhere?
So, I will be posting a link to each lecture on our Canvas page. So like after my student worker gets around to it, you'll see a link that should say like class meeting number 1 video up here above the in-class assignment or whatever. But then you could also go to my shitty YouTube channel where I have recorded literally everything I've taught for better or worse for the past several years, effectively since COVID started. How do I search for it? Yeah, so this is my shitty YouTube channel. It's literally just my last name lectures, and it's got all of the classes that I've taught for the last several years up there. So if you don't remember how to do some sort of circuit analysis technique, I have a shitty video on it, I'm sure of it. Yes.
So there's no like kit or anything for this course?
Nope.
For anything other than-
Nope. At this point, I have not developed any projects for this class because I just get busy and forget about it. So it's just a meat and potatoes lecture, homework, exam course. No kits, no projects or anything like that. Yep. Nope. And it needs to happen at some point, probably sooner rather than later, or Dr. Long is going to punch me in the face, but it hasn't happened yet. So any other questions or anything before we get cracking on math? All right, so what I want to do today is to just review complex numbers and then phasors and then phasor or frequency domain relationships so that we can get into analysis of single phase systems on next Tuesday. All righty. So what is a complex number? You guys are supposed to have had experience with it, not trying to throw shade at Ron or anything like that, just saying it shittily because I'm a jerk. What is a complex number? Sorry, what was that? Okay, so not necessarily a whole number, but it is a real number and then an imaginary number, all lumped together as a single number. Absolutely right. Okay. So I'm going to put a complex plane here in the middle of the screen. Okay. So in this complex plane, the real axis is the horizontal axis, and the imaginary axis is the vertical axis. And so we can express complex numbers in multiple different forms. So the first form that we are going to look at is what's called the rectangular form. And in a rectangular form, complex number is expressed as a real component and an imaginary component. So that might be something like lowercase a plus j lowercase b, where j is the imaginary operator that we're going to use. Let me put a little arrow here. J is simply equal to the square root of -1. So if we were to plot a complex number on our complex plane that was expressed in rectangular form, we would simply go out, let's say, lowercase a units in the real direction, and we would go up lowercase b units in the imaginary direction. So we might have something like this. Where the projection onto the real axis is lowercase a, and the projection onto the imaginary axis is lowercase b. So I'm going to go ahead and make a note of that over here on the left, right? So the real part of complex number a is lowercase a, and the imaginary part of complex number a is lowercase b. The j tells us which part is the imaginary part, but it is not itself part of the imaginary number. Okay. So this is nothing more than a two-dimensional vector, effectively, right? We have units in the real direction and units in the imaginary direction, and we're just going out. So this is just the exact same thing as if we were looking at an XY plane, where in this case, the X direction is for real numbers and the Y direction is for imaginary numbers. Realistically, actually, this is just two number lines where one of them is 90 degrees out of phase with the other one, which is exactly what a complex number is. Okay. So in addition to this rectangular form, we could also express a complex number in exponential form. as well as polar form. Okay. The exponential form and the polar form carry the exact same information. The exponential form is just a more formal representation, and the polar form is just kind of a shorthand notation. Okay? So let's talk about what those entail. So our complex number A as a vector has some length. And we're going to call this length the magnitude of A. And that's denoted by those vertical bars on the outside, or absolute value signs around a complex number tells us that we're looking at its magnitude or length. Complex number A also forms an angle that's measured from the positive real axis up to the complex number. And we're going to call this angle theta A. So taking these two pieces of information together, our exponential form complex number could be written as the magnitude of A e to the j theta A. And in polar form, this is just going to look like the magnitude of A angle theta A. Now, just as a side note here, the calculators that I have suggested, the TI-36, X, the Casio 115, and the Casio 991, they can interpret rectangular form complex numbers and polar form complex numbers only. If you try to put an exponential form complex number into one of these calculators, it will freak out and give you an error. There is literally no reason you would ever need to input an exponential form complex number because it is literally carrying the exact same information as a polar form complex number. You just keep the magnitude, keep the phase angle, and throw the rest of it away. Okay. So if you're ever given an exponential form complex number, you can convert to polar form very easily, and then you're off to the races using your calculator and all of that kind of good stuff. All right, so now let's talk about how we can switch back and forth between these forms, okay? So let's start by figuring out how to go from rectangular into exponential or polar, okay? So I hope that everybody can see that our complex number A simply forms a right triangle, right? And the length of that complex number A is just the hypotenuse of that right triangle, which means we get to use the good old Pythagorean theorem from like 8th grade math, right? So the magnitude of A is simply going to be the square root of lowercase a squared, which is the real part squared, plus lowercase b squared, okay? And we can explicitly state this as the real part of A squared plus the imaginary part of A squared. Okay. So that's our definition for our magnitude, just based on simple mathematical relationships that we should be familiar with. Our phase angle, theta A, can be expressed in multiple different ways. I'm going to choose to express it in terms of an arctangent or inverse tangent operation. Okay. So theta A is simply the inverse tangent of B over A, or more formally, the inverse tangent of the imaginary part of our complex number divided by the real part of our complex number. All right. So we now know how to express our polar form complex numbers or get polar form complex numbers from rectangular form complex numbers. So let's work the other way around, right? To go the other way around, we have to use a little bit of trig. So the real part of complex number A, expressed in terms of its polar form pieces, is going to be the magnitude of complex number A times the cosine of the angle theta A. And the imaginary part B will be the magnitude of imaginary number A, or excuse me, magnitude of complex number A, goodness gracious, sine of theta A. This actually brings us to a very interesting identity that is kind of fundamental to the field of electrical engineering. Okay. So if we look at this polar form representation, and then these two equations right here, what we can surmise from this is that e to the j theta is equal to cosine theta plus j sine theta. This relationship right here is known as Euler's identity, and it is effectively fundamental to the AC analysis of all circuits. Without going into too many of the details, effectively what this identity allows us to do is represent time domain signals like the voltage that's being provided by the receptacles in this classroom, which are AC voltages. It allows us to represent those time domain AC voltages as complex numbers, with the understanding that any of the math that we do with those complex numbers, if we just take the real part of that result, it will be the exact same thing as if we had worked all of our analysis in the time domain, okay? I'm not going to make you guys suffer through working any problems in the time domain. I just want you to be aware, if you want to see it, you can watch me suffer through it for about 40 minutes or so for a very simple problem on one of my Circuits 1 lecture videos. It is awful. It involves a ton of trig and calculus and all types of gross things, whereas this little nice, neat identity right here effectively turns all of that terrible trig and calculus into simple algebra that you guys have already been doing, okay? So Euler's identity is the most fundamental equation in electrical engineering, at least for the analysis of AC systems. So I just wanted to make you guys aware. All right, so we have all of these relationships here. Now I'm going to express to you why you need to upgrade from your peasant calculators with a simple example, okay? So let's say that I have a complex number x that is expressed in rectangular form as -5 plus j7. And I want to figure out what that complex number x would be in polar form, okay? let's use the relationships that we have dealt with here. So the magnitude of complex number x would be the square root of what? Yep. So -5 squared plus 7 squared. Too lazy to do that math in my head. Square root of 25 plus 49, square root of 74. Sorry, did not mean to write a Q. Theta x would be the inverse tangent of what? 7 over -5. Somebody put that in their calculator. I want an answer in degrees. -54. 0.462. I typically speaking carry it out to 3 decimal places, but that rounds up to 0.5, absolutely. Oh, and I forgot my degree symbol here. So, would it surprise you all to find out that this is not correct? It does not surprise you that it isn't correct. Why is it not correct then? Why are you not surprised by its incorrectness? Because the angle is negative. Absolutely. So if we were to plot x on the complex plane, or this is our real axis and this is our imaginary axis, we know that we should go out roughly 5 units to the left in the real direction because it's -5, and then 7 units up, which would be somewhere about here. So this is where, what the hell is happening? Seems like it's the projector is restarting. All right, give me just a minute to do some troubleshooting here. All right, we're back. Okay, sorry about that technical difficulty. Okay, so the rectangular representation of x is telling us that effectively this complex number should lie in the second quadrant. But the polar representation, as we just figured stuff out, is effectively telling us that it should lie in the fourth quadrant, right? So it would have a magnitude of some length, square root of 74, and then an angle of -54 degrees, which would be roughly down here somewhere. So it turns out that in this specific case, the angle that we were given is actually 180 degrees away from the true angle. So why do you think that happened? So the problem is that the calculator's arctangent function literally can't tell the difference between 7 over -5 and -7 over +5. So the arctangent operation for our calculators is programmed in such a way that it will always return an angle that is either in quadrant 1, so somewhere between 0 and positive 90 degrees, and quadrant 4, or somewhere between 0 and negative 90 degrees. Now, I don't know about you guys, but I feel like having to go through and explicitly check every angle to make sure that it agrees with the rectangular form representation would be a huge pain in the ass. Instead, if we use one of these calculators that was designed to do complex math for us, it can do that conversion in a single step and it will always get the answer correct, okay? So for those of you that already, how many of you guys have a TI like this? Not you. How many of you specifically have this TI calculator? Okay, so like 2 of you guys. All right, so what is the calculator that the overwhelming majority of you have that isn't that one? The Casio. Okay, so we'll look at this one first since most of you have it, right? So in order to do this conversion for us with this Casio 991, for those of you that have it, we need to press the menu button. And then we need to go to option 2 for complex. So that's setting our calculator into complex mode. Miss, your calculator is the other Casio, so it's going to be a little bit different in a second, but that part is the same. So now our calculator is in complex mode. So we would type in -5 plus 7. And then to get our imaginary operator, we press the engineering button. It's the one that says ENG. And now, for those of you with the Casio 991, you press the option button on the top left-hand corner and scroll down, and you have 2 options. The first converts a number into polar form, and the second option converts a number into rectangular form. So since we're trying to convert into polar, I'm going to press 1. And we get square root of 74, angle 125.537, which is exactly 180 degrees off of this -54 that we were told, right? So for those of you that have a Casio 115, you do not have the option button, just to be clear. The Casio 115s do not have the option button. So instead you press Shift-2, and that brings up the complex menu, which is what the option button is doing for the Casio 991. For those of us with the TIs, we don't have to worry about changing our mode or anything like that at all. So I'm just going to type in -5 plus 7. To get my imaginary operator I just press the pi key 3 times. Shift the pi key brings up that complex menu, and then I just scroll down to option 4, which converts it into polar form. And I get 8.602, which is the square root of 74 with an angle of 125.538 and all that kind of good stuff. So when we get around to working on the in-class assignment and all that kind of good stuff, if you have any questions about how to use your calculator, just flag me down and I will happily show you, because I know we went through it pretty quick. Yes, sir.
Okay, so now that, since this Casio is in complex mode, it's not gonna like change anything besides what I do complex mode. All the indicators should be fine.
So-
I can't get it out of complex.
You can't get it out of
I
complex
mean,
mode now?
I go to mode.
Press 1. Yeah, so the complex mode is for working with complex numbers. The 1 mode is the calculation mode. So like for those Casios, you can't do integrals and stuff like that when you're in complex mode. You can't do derivatives when you're in complex mode. Any negative number is going to show up with a phase angle of 180 degrees. So you're never going to get a negative sign anymore. It's always just going to be something angle 180. So it is important for you to switch back and forth between the modes as is necessary, which is why I don't like that calculator, because I'm lazy and I don't want to do that, and the TI doesn't make me. All right. So we have observed a pitfall of potentially doing these types of calculations by hand. And also by allowing our, I guess what I'm trying to say is getting a calculator that can do these conversions for us will make our lives significantly easier for all of the math that we're going to be doing for this class, right? The overwhelming majority of the time we're going to be doing or dealing with complex math. And so having a calculator that can do it without us having to think about every little individual step is going to make our lives significantly easier. Okay, so let's talk about mathematical operations. And realistically, I'm expecting you all to do all of these operations on your calculator, but I'm going to use some of these operations in identities and stuff later on. So I'm going to walk us through how they work. So let's start with the conjugate operation, which is the only operation that is specific to complex numbers. So I'm going to define the conjugate operation graphically first, and then we're going to talk about what it means for polar form complex numbers and rectangular form complex numbers. So once again, let's say that I have some complex number A, like so. The conjugate of A simply means that I flip this complex number across the horizontal axis. So A conjugate would be this guy down here. So let's talk about what that operation entailed. First, in terms of its rectangular coefficients, right? So we're still out some distance A in both forms, right? So over here on the right, I'm going to put A is equal to A, and we're going to add on to that. And then down here below it, I'm going to have A with an asterisk, where that asterisk denotes the conjugate operation. And we're also going to have an A. Now, I had to go up B units to get complex number A, and I had to go down B units so that I'm at negative B here. So that means that if A is A plus JB, the conjugate of A is simply A minus JB. So the conjugate operation on a rectangular form complex number just changes the sign on the imaginary part. That's literally all it does, okay? Now let's look at things in context of the polar form parameters, right? So the length of this guy is exactly the same. So in polar form over here, we can see that the complex number and its conjugate have the same magnitude. What's changing is the angle, right? So here we have an angle of positive theta A. Down here, we're going to have an angle of negative theta A. So in the context of a polar form or exponential form complex number, the complex conjugate operation simply means change the sign on the angle, right? So just to recap here, conjugate operation for rectangular form complex numbers means we change the sign on the imaginary part. For polar form complex numbers, it means we change the sign on the imaginary part. That's, excuse me, on the angle, and that's all there is to the conjugate operation. So before we move along from the conjugate operation, let's talk about what happens when I multiply a complex number by its complex conjugate, which is an identity that we're going to use a whole heck of a lot in this class. Okay. So what would happen if I had A conjugate multiplied by A? Let's look at this in the context of exponential form complex numbers, because that's where it's going to be easiest to see what happens. So it doesn't quite square. It's close, but not quite, okay? So we know from up here that A conjugate is the magnitude of A, and then we would have e to the negative j theta A if we were representing our complex number in exponential form. Okay. The complex number A by itself, without the conjugate operation, is just the magnitude of A times e to the positive j theta A. So that looks to me like the magnitude of A squared. So what happens when I multiply e to the negative j theta A by e to the positive j theta A? What happens when I multiply two exponentials together? The arguments add, absolutely right. So what is negative j theta A plus positive j theta A? 0. What's e to the 0? 1. So any complex number multiplied by its complex conjugate just gives us the square of the magnitude. Okay. Like I said, that's something that we're going to use in multiple instances, especially when we're dealing with complex power and all of that kind of good stuff here in a few days. All right. So I think we've got a good grasp on the conjugate operation. So now let's go to more generic operations. Let's start with addition. And let's say that I have some complex number A is lowercase a plus j lowercase b. Some complex number B is C plus j lowercase d, like so. If I want to add A and B together, what's that going to look like? Well, I'm going to have A plus JB plus C plus JD, and I'm going to add these exactly as if they were vectors. So the real parts are going to add together, and the imaginary parts are going to add together. Okay. So that should leave me with A plus C plus J B plus D. So when I add two rectangular form complex numbers together, I get a rectangular form complex number where the real parts have added together and the imaginary parts have added together. Nothing particularly wild or crazy there. Okay. Now let's look at subtraction, which is just addition, but there's a negative sign involved. Okay. So using those same complex numbers of A is equal to lowercase a plus JB, and B is equal to lowercase c plus JD, complex number A minus complex number B is going to look like A plus JB minus C plus JD, and I'm going to do effectively the exact same thing. So I'm going to distribute that negative sign. So I'm going to have A plus negative C. So that's just going to look like A minus C plus J, B plus negative D, or B minus D. like so. So once again, we see that when we have two rectangular form complex numbers and we subtract them in this case, we still wind up with a rectangular form complex number. Okay. Now let's look at multiplication, which will be a little bit more complicated. Using those same exact complex numbers again. All right, so before we go through the math involved here, I want to point something out. Whenever I'm going to ask you guys to multiply complex numbers, I am not going to include any sign that indicates multiplication. So let me explain what I mean, right? So typically speaking, if we wanted to multiply a couple of numbers together, we might see it expressed as something like this, like A times B, right? Now, the reason why I don't like to use that for like that cross symbol for multiplication dealing with complex numbers is because they are fundamentally vectors, and there is a cross product operation for vectors that literally does not have any meaning whatsoever for complex numbers, right? So I can't use an X sign because it might be confused as a cross product. I can't do A dot B because of the dot product operation, which also doesn't make any damn sense whatsoever for complex numbers. I can't do A asterisk B because you might get that confused with the conjugate operation. So I'm literally left with nothing but put the two numbers beside each other and hope that you guys remember that that means multiply. Okay, so that's why I'm writing it in that specific form. It's actually to make it the least confusing as possible. So anyway. All right, so we would have A plus JB multiplied by C plus JD. And so we're just going to FOIL this out like high school algebra. So I'm going to have A times C plus J A times D plus JB times C plus J squared B times D. So what's J squared? What? Okay, so what's I squared? -1, right? So this guy right here is just -1. So now we can lump together some things, right? So we have a real part that is AC, and then we also have another real part that is negative BD. And then for our imaginary parts, we have an AD, and we're going to add to that a BC. So this is what our multiplication operation looks like using rectangular form complex numbers. Once again, if we put in a rectangular form complex number, we get out a rectangular form complex number. Now, this is a little tedious. So instead, let's investigate what would happen if we used exponential form complex numbers or polar form complex numbers, right? We actually did this a few minutes ago when we multiplied A by A conjugate. So if I have complex number A is equal to the magnitude of A, e to the j theta A, and complex number B is equal to the magnitude of B, e to the j theta B, then complex number A times complex number B is going to look like the magnitude of A, e to the j theta A, times the magnitude of B, e to the j theta B. And from what we discussed earlier, those two magnitudes are just going to multiply, and those angles are simply going to add together. Sorry, I don't need that extra J there. So multiplication is a little bit easier to do with polar form complex numbers, or exponential form complex numbers, excuse me, than it is with polar form. Rectangular form. Oh my God, I bet you used so many wrong words there. Let's try that again. Multiplication is easier with exponential and polar form complex numbers than it is with rectangular form complex numbers, right? Just as a heads up, in polar form, this would simplify to the magnitude of A times the magnitude of B with an angle of theta A minus theta. All right, and now lastly, we have division, which, if I'm being honest, is an absolute pain in the ass in rectangular form, but we'll figure it out. So if I want to have A divided by B, that's going to look like A plus JB over C plus JD. Now, realistically, there's not anything technically wrong with this representation. However, it doesn't seem to work the same as all of the other mathematical operations. And let me explain what I mean by that. Okay? When we added two rectangular form complex numbers together, we got a single rectangular form complex number. When we subtracted two rectangular form complex numbers, we got a single rectangular form complex number. When we multiplied two rectangular form complex numbers, we got a single rectangular form complex number. But here, when we divide, we get a ratio of rectangular form complex numbers instead of a single complex number. That seems a little wonky. So in order to fix that, we are going to have to multiply both sides of this expression by a fancy version of the number 1. Okay? So what I'm going to do is I'm going to multiply by B conjugate over B conjugate. So recall that B conjugate means I just change the sign on the imaginary part. So that's going to look like C minus JD. So what should B conjugate times B come out to? The magnitude, come back up here, of B squared. The magnitude of B is the square root of C squared plus D squared. And I square that magnitude, it's just going to give me C squared plus D squared, right? So I'm going to have in my denominator C squared plus D squared. Now let's work on the numerator. So I'm going to have A times C. Then I'm going to have minus J A times D plus J B times C minus J squared B times D. And now I'm going to lump the real parts together. So what's negative J squared? Positive 1, because J squared is negative 1, so negative J squared is positive 1, right? So I'm going to actually have AC plus BD over C squared plus D squared plus J BC minus AD over C squared plus D squared. And now I have a form that I'm expecting a single rectangular form complex number. Like I said, this is a bit of a pain in the ass. Okay? Instead, if we used exponential or polar form complex numbers, this will come out in a much simpler fashion. So A over B is going to look like magnitude of A e to the j theta A over the magnitude of B e to the j theta B. So those magnitudes, we're just going to have the ratio, and then it'll be e to the j theta A minus theta B. And in polar form, this simplifies to the magnitude of A, sorry, these shouldn't be magnitude signs here, over the magnitude of B with an angle of theta A minus theta B. Yes. Yeah, this one right here should be plus. Thank you for that. Yeah. Nope, nope, you were correct. Like I said earlier, I'm a jackass. I make mistakes constantly. If something seems sketchy, let me know. Chances are it's my mistake. So up here in polar form, I accidentally had theta A minus theta B instead of theta A plus theta B. So up here where it's theta A plus theta B, it needs to be the same thing down here. Just like over here where we have theta A minus theta B, it needs to be theta A minus theta B. Absolutely. Thank you for that. All right, so that is complex numbers. Anybody have any questions, comments, or concerns before we revisit phasors? So how to go from polar to rectangular on the calculator. Okay, so which calculator do you have? 36X. Okay, so if you press second and pi, and then you scroll down to option 5, that's converting from polar to rectangular. So if it has triangle A plus BI, that's saying convert it into that A plus BI form. How do you get the angle symbol? The very first option on the complex menu there. So second pi and then option 1. Like I said, I'll be more than happy to answer any questions about how to use your calculator effectively after we wrap up the lecture and all that kind of good stuff. Any other questions? Yes, sir. Uh-huh. Yeah. I don't presently because I don't have a camera that I can just aim at the calculator or whatever. I've talked through it so all of my lectures on complex numbers, I talk the way through it and tell you what buttons to press and all that kind of stuff. Once you get the calculator in, or if you want to pop over to my office immediately after class, so I can just let you borrow one of these until you're able to get your own. Easy to go. Yeah. Mm-hmm. All right. So let's talk about phasors. Okay, so let's say that I have a sinusoidal voltage waveform that is expressed in the form Vm, where this is just the magnitude of our sinusoidal function, times the cosine of some angular frequency omega times t plus some phase angle theta v. And while we're at it, let's go ahead and introduce a current waveform as well. Im cosine omega t plus theta I. So I want to point something out here. Omega in both of these waveforms is the same. So both the voltage and the current are oscillating at the exact same angular frequency. However, the magnitude of the sinusoidal signals can be different. The phase angle of the sinusoidal signals can be different, but the frequency has to be the same. Okay? So these are what we would call a time domain representation of a signal. Well, these signals are nothing more than the real part of a complex representation of this signal, right? So earlier, when I introduced Euler's identity, the cosine part was the real part. So this time domain signal is simply the real part of Vm e to the j omega t plus some phase angle theta v. And that current waveform is just the real part of Im e to the j omega t plus theta I. So we can observe something fairly interesting here, or at least interesting to me. I'm a big dork who loves electrical engineering. This complex number, this exponential form complex number representation of these signals carries the exact same information, right? It has the same magnitude, it has the same angular frequency omega, it has the same phase angle theta as well. So all of the information is there, but the real part, the part that comes out of our outputs and all of that kind of stuff, is just the real part of this complex number, okay? So we're going to call this representation here as mixed domain signals. I'm calling it mixed domain. This is something that I've just made up because there's still an obvious dependency on time because there's a t in there and all of that kind of good stuff. But we're leaning more towards the frequency domain, which is where phasors live and operate, okay? So this is kind of like an intermediary step to go from a time domain signal to a phasor, okay? So let's finally wrap things up by taking one further step. So our phasor voltage V and our phasor current I are simply going to be those mixed domain signals expressed in polar form, where we just throw away the e to the j omega t part. So we're just going to have a magnitude and a phase angle, and we're not going to worry about the bit that we threw away. Now here in a few minutes, actually we might do it in on next Tuesday's class because I'm talking more than I intended to do today, but that's okay. We're going to see effectively why we get to throw away that e to the j omega t part. Okay? But for now, let's just take it on faith that that's going to be okay. So I do want to point something out. Oh, actually, before I do this, So these are frequency domain signals, which are commonly referred to as phasers. So what I was alluding to a moment ago is that we are dealing with everything with the cosine function as the fundamental basis here, right? So if I have a time domain signal that I can express as a cosine function, that is what allows me to express it as a mixed domain signal where we have the real part, which then allows me to go one step further and throw away the e to the j omega t bit, allowing me to express it as a phasor. If instead I had a sine function instead of a cosine function, I would need to convert that to a cosine in order to correctly construct my phasor representation. Okay? So let's do a few simple examples here. And let's actually do in-class assignment problem 2 together. Since we're going to run out of time to do. All right, so we're going to look at problem 2. And I think that'll be effectively the last thing that we're going to do today. All right, so in this problem, we are asked to express the following time domain signals as phasors with positive magnitudes in the frequency domain. Okay, so if we look at part A here, where we're given VA of t is equal to -10 cosine 4t plus 75 degrees volts. Effectively, we're almost exactly where we need to be to just throw away or to convert directly into a phasor. The only real issue that we have is that we were told that we want things to have positive magnitudes. So how do you guys think we're going to get rid of that negative sign out front? So we can either add or subtract 180 degrees from our phasing. Okay, so that is a simple trig identity. So I'm going to go ahead and write that down because I will expect you all to remember that one. So this is just a trig identity. If we have negative cosine omega t, this is the exact same thing as positive cosine omega t plus or minus 180 degrees. Okay, it literally does not matter if you add or subtract 180 degrees. We are just going halfway around the unit circle either way. Okay. So applying this identity, we would then have 10 cosine 4t. So I'm going to subtract 180 degrees from this. So 75 minus 180, if I'm not mistaken, comes out to be negative 105 degrees. Okay. So now I have my magnitude expressed as a positive number. I have my phase angle. It's expressed in terms of the cosine function. So I'm good to go. So what should my phasor representation of this voltage be? 10 angle, negative 105. We keep the magnitude, we keep the phase angle, we throw the rest away. Okay. Now let's look at part B. So for part B here, we have a signal 5 sine 20t minus 10 degrees volts. So I'm going to have to introduce another trig identity for you guys. And this identity is that the sine of omega t is equal to the cosine of omega t minus 90 degrees. So effectively, in order to convert from a sine function into a cosine function, we simply subtract negative 90 degrees. Oh goodness, we subtract 90 degrees from the phase angle, okay? So applying this identity, we would have 5 cosine 20t, and then negative 10 minus 90 comes out to be negative 100 degrees. I'm sorry, what was that? So we're not trying to get rid of a negative sign, so no. Yep, yeah, so all we're doing is we're converting the cosine to a sine. There's no negative sign to worry about, so we just apply this one single identity. And you're absolutely correct. It's just going to come out to be 5 angle negative 100 degrees. And now we'll do part C. So part C, we have a voltage waveform that is 4 cosine 2t plus 25 degrees plus 3 sine 2t volts. So this one is significantly more tricky, right? If we were to do all of this in the time domain, it would be an absolute nightmare. So we're going to start in the time domain, and then we're actually just going to substitute each part's frequency domain in, and then do all the math in the frequency domain to make it come out to be something less terrifying, right? So this first term here is already in the form that we want. We have a positive magnitude, we have a cosine function, we have some phase angle, right? So the 4 cosine 2t bit is going to get left alone. How are we going to change that 3 sine 2t into a cosine function? Minus 90 degrees, right? So that's going to look like 3 cosine 2t minus 90 degrees. When we're dealing with voltages and currents specifically, no. So the angular frequency there, so that's the bit that's being multiplied by t, is going to be extremely important when we're looking at impedances, specifically for inductances and capacitances. Because the impedance of an inductor and a capacitor is frequency dependent. The voltages and the currents, it's not really a thing. But once we're looking at impedances, which is the next topic that we're going to talk about at the beginning of class on Tuesday, because of how much time we have left, those angular frequencies will become extremely important. So for voltages and currents, we're allowed to just throw them away. And we're allowed to do that effectively because we know that if one thing in our circuit is excited at this frequency, then everything in our circuit is excited at that same frequency. So for voltages and currents, it's effectively just redundant information, which is why we don't need to keep carrying it around all over the place. But impedances, it'll become pretty darn important pretty quick. All right. So what I'm going to do here is I'm just going to convert both parts of this into phasors and then add those phasors together to express it as a single phasor, right? So what's the 4 cosine 2t plus 25 degrees bit going to look like as a phasor? 4 angle positive 25. What's the 3 cosine 2t minus 90 degrees bit going to look like as a phasor? 3 angle negative 90 degrees. Absolutely right. And so now we're at a point where we can literally just throw this bit in our calculator and get a single polar form phasor out, right? So if I put in my calculator 4 angle 25 plus 3 angle minus 90, I got 3.854 with an angle of negative 19.861 degrees. Yes. Sure. All right. So I will help you guys in just a second. This is the end of what I wanted, or it's actually not the end of what I wanted to cover today. It's the end of what I'm able to cover today. We'll talk about impedance and all that kind of stuff as the first thing on next Tuesday's class meeting, which means realistically, you guys should be able to do it based on the fact that you've had that material before in Ron's class. But if you don't want to do it, that's okay. So effectively, you don't necessarily need to worry about problem 3 literally at all. We just did problem 2 together. Problem 1 is an exercise, is an exercise for using your calculator. So from here on out for the next half hour or so, I'm just going to answer questions. Okay, I'm done with the lecture. So if you guys are comfortable, you're free to jet. If you want to stay and ask questions, please do. All right, now let's sort this out.